Close your eyes if you'd like, or let them rest gently on nothing in particular. There's no need to concentrate on what comes next. You don't need to remember any of this, and you don't need to understand it all at once. What we're going to explore together is simply a story about the world, about the way things are, told slowly and carefully, with no rush at all. It's a story about quantum decoherence, which sounds like a complex phrase, and in some ways it is, but really it's just a name for something quite natural, something that's happening all around you, all the time, even now as you settle into comfort and stillness. Quantum decoherence is about how the quantum world, that strange realm of tiny particles and waves and probabilities, becomes the ordinary world you see around you. It's about how the weirdness of the very small gives way to the solid, predictable reality of tables and walls and the gentle weight of blankets. But we'll get to all of that slowly, very slowly, because there's no hurry at all. Let's begin somewhere simple and familiar. Let's begin with light. You know what light is, of course. It fills the day, it reflects off surfaces, it lets you see colors and shapes. For most of human history, light was simply light, nothing more mysterious than that. It came from the sun, from fire, from the moon's reflected glow. But a few hundred years ago, people began to wonder more carefully about what light actually was, about its true nature, and they discovered that it wasn't quite as simple as it seemed. Some thought light was made of tiny particles, little pellets of brightness that flew through space. Others thought it was a wave, like ripples on water spreading outward from its source. And for a long time these two ideas seemed to be at war with each other, each explaining some things but not others. If you don't follow all of this right now, that's perfectly fine. Just let the words wash over you. There's a gentle rhythm to this story, and you can drift with it however you like. By the early 1900s, scientists had done enough experiments to realize something extraordinary and strange. Light, they discovered, was somehow both. It could behave like a particle in one situation and like a wave in another. This wasn't a mistake or a confusion. It was simply how light was, and not just light, they soon found. Electrons, those tiny components of atoms, also behave this way. So did atoms themselves. So did eventually everything, though the effect becomes harder to see as things get larger. This discovery marked the birth of quantum mechanics, which is the name we give to the rules that govern the very small. And quantum mechanics is strange, stranger than almost anything else we know about. But it's also extraordinarily accurate. It describes the world as it truly is, at least at these tiny scales, with astonishing precision. You don't need to know the equations or the mathematics. What matters, for our purposes, is simply the strangeness, the peculiarity, and then eventually how that strangeness fades away and becomes the familiar world you know. In the quantum world, things exist in what we call superposition. That's a word you'll hear again, so don't worry if it doesn't settle in your mind just yet. Superposition means that something can be in multiple states at once, at least until you look at it, until you measure it, until something interacts with it in the right way. A quantum particle can be here and there, spinning this way and that way, all at the same time. Not that it's undecided, not that we simply don't know which it is, but that it genuinely is all of those things simultaneously, woven together in a kind of blended possibility. This sounds impossible, and in the world of everyday objects it is impossible. A book is on the table or on the shelf, not both. A cat is awake or asleep, not both. But in the quantum realm, before measurement, before observation, the rules are different. Things hover in this state of multiple possibilities, and only when they're measured, only when they interact with something larger, something that counts as an observer, do they collapse into a single definite state. That's what the old Copenhagen interpretation of quantum mechanics told us, and for a long time that was where the explanation ended. Measurement collapses the wave function, they said, and the quantum strangeness disappears. But that explanation always left something unsatisfied, something unfinished. What counts as a measurement? What is an observer? Does it have to be a person? Does it have to be conscious? And why should the universe care whether someone is looking? These questions bothered people, thoughtful people, for decades. And slowly, gradually, another answer began to emerge, an answer that didn't require consciousness or observers or any special act of looking. That answer is decoherence. Decoherence is the process by which quantum systems lose their quantum behavior, their superposition, their strangeness, simply by interacting with their environment, not because they're being watched, but because they're touching other things, bumping into particles, exchanging energy with the world around them. And the world around them is big, unimaginably big compared to a single quantum particle, full of countless other particles, all jostling and interacting and creating a kind of noise, a kind of background hum that washes away the delicate quantum coherence. Coherence, that's another word we'll return to. Coherence is what we call it when quantum states stay synchronized, when the different possibilities in a superposition maintain their relationship to each other, their phase relationship, like waves that rise and fall together in a coordinated pattern. When coherence is preserved, quantum effects persist. When coherence is lost, when decoherence happens, the quantum behavior fades and classical behavior, ordinary behavior, emerges. You don't need to hold on to all of these words. They'll come back around again and again in slightly different ways. For now, just rest in the idea that there's a process, a natural process, that turns the quantum into the classical, the strange into the familiar. And it happens not because of anything magical, but simply because things interact, because the world is full and busy and constantly exchanging information at levels too small to see. Let's slow down even more and think about what it means for something to be in superposition. Imagine, if you like, a single electron. It's so small you can't see it, even with the most powerful microscope, but it's there, and it has properties. One of those properties is something called spin. Spin is a bit like the electron rotating, though it's not really rotating in the way a top rotates. It's a quantum property, intrinsic, fundamental, and it can be in one of two states, spin up or spin down, we say, pointing one way or the other. Now, in the quantum world, before we measure this spin, the electron doesn't have a definite spin direction. It's in a superposition of both spin up and spin down, both at once, blended together. If we were to write this mathematically, which we won't, we'd say it's in a combination, a sum of both possibilities, each with a certain weight, a certain probability. But we don't need the math, we just need the image, the idea. This tiny particle exists in both states until something causes it to become one or the other. When we measure the spin, we get a definite answer. Spin up, let's say, and from that moment on, the electron is spin up. The superposition has collapsed. But here's the deep question that bothered physicists. Why? What happened in that moment of measurement? What made the electron choose? The old answer was that the act of measurement itself caused the collapse, that our detector, our instrument, our consciousness, perhaps, forced the electron to pick a side. But this answer was never quite satisfying, because it made the universe seem to depend on us, on observers, in a way that felt arbitrary and strange. And so people kept searching for a better explanation. Decoherence offers that better explanation, though it's subtle, and it takes time to appreciate. The idea is this. The electron isn't really isolated. It's surrounded by other particles, by photons of light, by molecules in the air if it's in air, by the atoms of the measurement device if it's being measured. And all of these other particles are constantly interacting with the electron, however faintly, exchanging tiny amounts of energy, scattering off it, becoming entangled with it. Entanglement is another key idea, one we'll circle back to many times. Entanglement means that two quantum systems become linked in such a way that the state of one depends on the state of the other, even if they're far apart. When the electron in superposition interacts with a photon, let's say, the photon becomes entangled with the electron's state. If the electron is spin up, the photon goes one way. If the electron is spin down, the photon goes another way. And now the photon carries information about the electron's state out into the world. But the photon doesn't just carry it to one place. It might scatter off other particles, which scatter off still others, and very quickly, incredibly quickly, the information about the electron's state has spread out into the environment, into countless particles, all of which are now entangled, however weakly, with the original electron. This spreading, this leaking of information into the environment is decoherence. From the perspective of the electron, it still exists in superposition in some sense, but from the perspective of us, or any measurement device, or anything else in the ordinary world, the superposition has become invisible. The different parts of the superposition, spin up and spin down, have become correlated with different environmental states, and those environmental states are so complex, so tangled, involving so many particles, that we can never untangle them. We can never bring them back together to see the quantum interference, the quantum weirdness that superposition would allow. And so the electron appears to us to be in one definite state, even though in the deepest sense, the full quantum description still includes both possibilities, now entangled with the entire environment. This is why decoherence is sometimes called environment-induced decoherence. It's the environment, the surroundings, that washes away the observable quantum effects. You might feel yourself drifting as you listen to this, and that's exactly right. There's no test, no quiz, no need to retain every detail. The ideas will return, each time a little clearer, a little more familiar, like a melody you've heard before but never quite learned. Let's think about time for a moment. How fast does decoherence happen? The answer depends on the system and its environment. For a single electron in empty space, far from anything else, decoherence would be incredibly slow, perhaps non-existent. But for an electron in a laboratory, surrounded by apparatus, by air molecules, by stray photons, decoherence happens almost instantly, in tiny fractions of a second, far too fast for us to notice. For larger objects made of many particles, decoherence happens even faster because there are more interactions, more ways for information to leak out into the environment. This is why we never see macroscopic objects, everyday objects, in superposition. It's not that the laws of quantum mechanics stop applying to them. The laws are still there, still in effect. It's just that decoherence is so fast, so efficient, that the superposition is washed away before it can ever be observed. A baseball isn't in two places at once, not because quantum mechanics fails at that scale, but because decoherence prevents us from ever seeing such a state. The environment is constantly measuring the baseball, in a sense, constantly interacting with it, constantly destroying any quantum coherence it might briefly possess. This explains something that puzzled people for a long time, why the quantum world seems so different from the classical world, even though everything is ultimately quantum. The answer is decoherence. The classical world emerges from the quantum world through the process of decoherence, through the unavoidable interaction of systems with their environments. Now let's wander a bit into history, into the people who thought about these things, because science is not just ideas floating in the void, but people, human beings, struggling to understand, arguing, making mistakes, slowly finding clarity. The story of quantum mechanics begins in the early 20th century with figures like Max Planck, who first suggested that energy might come in discrete chunks, quanta, rather than continuous flows. Then Albert Einstein, who explained the photoelectric effect by treating light as particles, photons, even though light was supposed to be a wave. Then came Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Wolfgang Pauli, and others. A generation of brilliant minds who built the framework of quantum mechanics in the 1920s and 30s. They discovered the equations, the principles, the strange rules that govern atoms and particles. But they also argued, deeply and passionately, about what it all meant. What was really happening in the quantum world? What was the nature of reality? Bohr and Heisenberg developed what came to be called the Copenhagen interpretation, which said, roughly, that quantum mechanics is complete as it stands, that particles don't have definite properties until they're measured, and that it's meaningless to ask what's happening when no one is looking. Measurement causes collapse, they said, and that's the end of it. This view became the dominant orthodoxy for many years, taught in textbooks, accepted by most physicists. But others were never satisfied. Einstein famously resisted, insisting that there must be something deeper, some hidden variables, some underlying reality that quantum mechanics was failing to capture. He didn't like the idea that God played dice, that the universe was fundamentally random. Schrödinger, too, was troubled, and he created his famous thought experiment with the cat, Schrödinger's cat, to show how absurd it seemed to apply quantum superposition to everyday objects. A cat in a box, he imagined, whose fate is tied to a quantum event, and so the cat is both alive and dead until someone opens the box and looks. He meant this as a criticism, as a way of showing that something was wrong with the interpretation, but it became instead one of the most famous illustrations of quantum strangeness. For decades, the measurement problem, as it was called, remained unresolved. What exactly is measurement? When does collapse happen? These questions seemed almost philosophical, perhaps unanswerable by science. But gradually, people began to realize that the environment might hold the key. If you include the environment in your quantum description, if you don't pretend that a particle or a system is isolated, but instead account for all the things around it, then something interesting happens. You find that the strange quantum correlations, the interference effects, the coherence, all of it becomes hidden, buried in the complexity of the environment. The term decoherence and the full development of the theory came later, mostly in the 1970s and 80s, through the work of physicists like H. Dieter Zeh, Wojciech Zurek, and others. They showed, with careful mathematics and reasoning, that decoherence was not just a minor effect, but a central part of understanding how the quantum world relates to the classical world. They showed that it happens naturally, inevitably, whenever a quantum system interacts with a large environment. You don't have to remember these names, of course. Just let them pass through your awareness like clouds drifting across a quiet sky. The point is simply that these ideas took time to develop, that they emerged slowly from decades of thought and questioning, and that they represent a kind of resolution, though not a final one, to some of the deepest puzzles in physics. Let's return now to the idea of entanglement, because it's so central to decoherence, and it's worth understanding gently, patiently. Entanglement is one of the most distinctive features of quantum mechanics, something that has no real parallel in the everyday world. When two particles become entangled, their states become linked in such a way that you can't describe one without describing the other. They form a single quantum system, even if they're separated by large distances. Imagine two electrons that interact briefly and then fly apart. After the interaction, they're entangled. If you measure the spin of one and find it spin up, you'll instantly know that the other is spin down and vice versa. This isn't because they agreed on a signal beforehand, not because one sent a message to the other. It's because they share a single quantum state, a single wave function that describes both of them together. Einstein called this spooky action at a distance, and he was deeply uncomfortable with it. It seemed to violate the principle that influences can't travel faster than light. But many experiments over many years, have confirmed that entanglement is real, that the correlations it predicts truly exist, and yet strangely you can't use entanglement to send information faster than light. The correlations are there, but they're only revealed when you bring the measurement results together and compare them, which has to happen through ordinary slower-than-light communication. Now, in decoherence, entanglement plays a crucial role, but in a different way. When a quantum system interacts with its environment, it becomes entangled not with one or two particles, but with an enormous number of them, effectively with the whole environment. And this is what makes the superposition unobservable. The different parts of the superposition become correlated with different environmental states, and because the environment is so large, so complex, we lose track of those correlations. We can't measure the environment precisely enough to recover them. This is sometimes called losing information to the environment, though the information isn't truly lost in a fundamental sense. It's just spread out, dispersed among countless particles, rendered effectively inaccessible. And because we can't access it, we can't see the quantum interference that would reveal the superposition. Instead, what we see is a classical mixture, a situation where the system appears to be in one state or the other, with certain probabilities, but not both at once in a way we could detect. There's a technical term for this if you're curious, though you needn't hold on to it. We say the system's density matrix, which is a mathematical object that describes its quantum state, becomes diagonal in a certain basis. That basis is called the pointer basis, the set of states that are stable under decoherence, the states that the system appears to collapse into. But again, this is just language, just a way of describing what's happening. The essence is simpler. The environment picks out certain states as special, as the ones that survive decoherence, and those are the states we observe as classical outcomes. Let's think about an example. Something concrete but simple. Imagine a single photon, a particle of light, traveling through space. It has a polarization, a direction in which its electric field oscillates. It could be vertically polarized, horizontally polarized or in a superposition of both. If we send this photon through certain kinds of crystals or filters, we can manipulate its polarization, put it in superposition, and observe quantum interference effects. But now imagine this photon is traveling through air or through a piece of glass. Along the way, it might scatter off molecules, interact with the material, exchange energy. Each interaction entangles the photon's polarization state with the state of the environment, with the molecule it scattered from, with the other photons that might be present. Very quickly, the coherence between the vertical and horizontal polarization states is lost. The photon still has a polarization, but the superposition has decohered. It now appears to be either vertical or horizontal, not both, and we can no longer observe the interference that superposition would produce. This happens all the time, constantly, to every photon, every particle, every system that isn't perfectly isolated. And perfect isolation is impossible in practice, or at least extraordinarily difficult. Even in the best laboratories, even in the most carefully controlled experiments, some interaction with the environment is unavoidable. The air can be pumped out, creating a vacuum. The temperature can be lowered to reduce thermal noise. Shielding can be used to block stray photons. But there's always something, some residual interaction, and so decoherence is always present, always working to wash away quantum effects. This is why quantum computers are so challenging to build. Quantum computers rely on maintaining coherence, on keeping quantum bits, qubits, in superposition and entangled with each other, so they can perform computations that classical computers can't. But decoherence is the enemy of this. The qubits interact with their environment, and the quantum information leaks away, causing errors. Engineers and physicists have to work incredibly hard to isolate the qubits, to reduce decoherence, to keep the quantum state alive long enough to complete a computation. They cool the systems to temperatures near absolute zero. They use sophisticated error correction techniques. They design qubits that are less sensitive to environmental noise. And even then, it's an ongoing battle against decoherence. But for the world around us, for the ordinary macroscopic world, decoherence is not a problem. It's a blessing in a way. It's what gives the world its stability, its definiteness, its classical character. Without decoherence, everything would be in superposition. Everything would be blurred and uncertain, and we couldn't have the kind of stable structures, the reliable cause and effect, that make life and consciousness possible. So in a deep sense, we owe our existence to decoherence, to the fact that quantum weirdness fades away at the scale of tables and chairs and people and planets. Let's drift for a moment into the philosophical, the cosmic. What does it mean that the universe is fundamentally quantum, that at its deepest level, reality is made of superpositions and entanglement and probability amplitudes, and yet we experience a classical world, a world of definite outcomes and solid objects? Decoherence offers a kind of bridge, a process that connects the two, but it doesn't answer every question. One question that remains is the question of the wave function collapse itself. Decoherence explains why we don't see superpositions, why they become invisible, effectively classical. But does it explain why, in each individual case, we get one outcome and not another? Why, when I measure an electron's spin, do I get spin up rather than spin down, or vice versa? Decoherence makes the probabilities emerge, makes the appearance of collapse happen, but some would say it doesn't fully solve the measurement problem, because it doesn't tell us why a particular outcome occurs. There are different views on this. Some physicists say that decoherence, combined with the many worlds interpretation, does solve the problem completely. In the many worlds view, the wave function never collapses at all. Instead, every possible outcome actually happens, each in a different branch of reality. When I measure the spin, the universe splits, in a sense, into two branches, one where I see spin up and one where I see spin down. Both are real, both exist, but they decohere from each other, they can't interact, and so I experience only one branch at a time. This is a strange idea, perhaps the strangest in all of physics, and you don't need to believe it or even fully understand it. Just let it sit in your mind as one possibility, one way of making sense of the quantum world. The many worlds interpretation removes the need for collapse entirely. Decoherence explains why the branches don't interfere with each other, why we experience a definite outcome even though all outcomes occur. It's a complete picture, some would say. though others find it extravagant, multiplying universes beyond necessity. Other interpretations exist as well. There are hidden variable theories, which suggest that particles have definite properties all along, but those properties are governed by deeper variables we can't yet see. There are objective collapse theories, which propose that the wave function actually does collapse, randomly, due to some physical process we haven't fully understood yet, perhaps related to gravity or to the complexity of large systems. Each interpretation has its advocates, its strengths, its challenges. For our purposes, for this gentle exploration, we don't need to choose between them. What matters is understanding decoherence itself, the process, the mechanism, the way it works, and decoherence is accepted by nearly all physicists, regardless of their interpretational preferences, because it's a straightforward consequence of applying quantum mechanics to systems and their environments. It's not speculative or controversial, it's just what happens when you do the calculation, when you include the environment in your quantum description. Let's think about scale again, about size. Why do small things show quantum behavior more readily than large things? Part of the answer is decoherence, but there's also something more fundamental. Quantum effects, like interference and superposition, depend on coherence, on the different parts of the wave function maintaining a precise relationship to each other. And that precision is fragile. The more particles you have, the more complicated the system, the harder it is to maintain coherence, because there are more ways for interactions to scramble the phases, to disrupt the delicate quantum relationships. A single atom can be put in superposition relatively easily, isolated in a trap, laser-cooled, manipulated with precision. A molecule is harder because it has more internal states, more ways to interact with light and fields. A virus particle, though still tiny by everyday standards, is vastly more complex, made of billions of atoms, and keeping such a thing in superposition would require extraordinary isolation, far beyond what we can currently achieve. And a cat, or a person, or a planet, these are so large, so full of particles, all jostling and interacting and entangled with their environments, that quantum coherence is impossible. Decoherence happens essentially instantaneously. There's a beautiful piece of mathematics that describes this, though we won't go into the details. It's called the decoherence timescale, and it's a measure of how long a system can maintain quantum coherence before it's lost to the environment. For a dust particle in air, this timescale is extraordinarily short, perhaps a tiny fraction of a second. For a single atom in a good vacuum, it might be seconds or minutes or longer. For a molecule in a solution, it's typically very fast, which is one reason why quantum effects in biological systems, if they exist at all, are so hard to study and so controversial. Some people have wondered whether quantum effects play a role in biological processes, in photosynthesis perhaps, or in bird navigation, or even in the workings of the brain. There's some evidence for quantum coherence in certain biological systems, though it's still a matter of active research and debate. If it's real, if biology does exploit quantum mechanics in some way, then it must have evolved mechanisms to protect against decoherence, to maintain coherence long enough for the quantum effect to matter. This is speculative, fascinating, but not yet fully understood. You might feel your thoughts wandering, your attention drifting in and out, and that's perfectly natural. There's no need to follow every word, every sentence. The ideas are here, and they'll be here, circling back, repeating gently like waves on a shore. Let's return to the idea of measurement, because it's so central, and because decoherence changes how we think about it. In the old Copenhagen interpretation, measurement was a primitive concept, something you couldn't really define more precisely. You knew it when you saw it. A measurement was when you used a piece of apparatus, a detector, something macroscopic, to observe a quantum system. And at that moment, the wave function collapsed and you got a definite result. But this left awkward questions. What counts as a measurement? If I measure an electron with a detector, that's clearly a measurement. But what if the detector is small or poorly isolated? What if I measure the detector with another detector? At what point does the collapse happen? Is it when the electron interacts with the first atom of the detector, or when the signal reaches the readout screen, or when a human looks at the screen? These questions seemed unanswerable, or at least arbitrary. Decoherence offers a different perspective. It says that measurement is not a special separate process, but just a particular kind of interaction, an interaction between a quantum system and a much larger environment. An environment that includes the measuring apparatus and often much more. When the system interacts with this environment, it becomes entangled and the superposition decoheres. The environment, in effect, measures the system constantly and automatically, without any need for consciousness or human intervention. This removes the mystery in a way. There's no sharp line between measurement and non-measurement, no special moment of collapse. Instead, there's a gradual process of decoherence, which happens faster or slower depending on the system and its environment. For all practical purposes, for macroscopic systems, this process is so fast that it appears instantaneous, and we see what looks like a definite outcome. This is sometimes called the FAP approach, which stands for all practical purposes. For all practical purposes, the wave function has collapsed. The system is in one state, and we can treat it classically. But in principle, in the full quantum description, the superposition still exists, now entangled with the environment, too complex to ever observe directly. Some find this satisfying, a naturalistic explanation that doesn't require observers or consciousness. Others feel it's incomplete, that it doesn't explain why we experience one outcome rather than another, why there's a fact of the matter about which branch of the wave function we're in. But even those who want more from an interpretation of quantum mechanics generally accept decoherence as part of the answer, as an essential piece of the puzzle. Now let's think about what decoherence means for the universe as a whole, for cosmology. The universe, in its earliest moments, was a hot, dense soup of particles and radiation, all interacting intensely. As it expanded and cooled, structures began to form, galaxies, stars, planets, eventually life. Throughout this process, quantum mechanics was at work, governing the behavior of particles, the formation of atoms, the fluctuations in the early universe that seeded the large-scale structures we see today. But as the universe evolved, as things grew and cooled and became more complex, decoherence became more and more important. The quantum fluctuations in the early universe, tiny variations in density and temperature, were initially coherent, genuinely quantum. But as the universe expanded, as these fluctuations grew and interacted with the surrounding matter and radiation, they decohered. They became classical inhomogeneities, density variations that could grow under gravity into the galaxies and clusters we observe. This is a profound idea. The large-scale structure of the universe, the distribution of galaxies across billions of light-years, has its origin in quantum fluctuations, tiny quantum events magnified to cosmic scales. But those quantum events decohered early on, becoming classical, so that by the time galaxies formed, the process was entirely classical, described by gravity and fluid dynamics and other familiar physics. Decoherence also plays a role in black holes, though here the story is more speculative. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They have an event horizon, a boundary beyond which information is lost to the outside universe, at least classically. But quantum mechanics suggests that black holes aren't entirely black. They emit radiation, called Hawking radiation, and they eventually evaporate. This raises deep questions about information, about whether information that falls into a black hole is truly lost or somehow preserved. Decoherence might be part of the answer, though the details are still being worked out. When something falls into a black hole, it interacts with the black hole's environment, with the radiation and particles near the horizon, and this interaction might cause decoherence. The information becomes entangled with the environment, perhaps spread out in the Hawking radiation, encoded in subtle correlations that are difficult or impossible to retrieve. This is still an area of active research, one of the frontiers of theoretical physics, where quantum mechanics and gravity meet, and where our understanding is still incomplete. But you don't need to worry about these complexities. Just rest in the idea that decoherence is a universal process, happening everywhere, at all scales, from the smallest particles to the largest structures in the cosmos. It's what makes the universe intelligible, what allows classical physics to emerge from quantum foundations, what gives the world its stability and structure. Let's slow down even more and think about time again, about the flow of time, about the way the future unfolds from the past. In classical physics, Time is straightforward. The state of the world at one moment determines, at least in principle, the state at the next moment. If you know the positions and velocities of all the particles, you can calculate their future trajectories. Time flows forward, and the future is determined by the past. In quantum mechanics, things are more subtle. The wave function evolves in time according to a precise equation, the Schrödinger equation, and this evolution is deterministic. If you know the wave function now, you can calculate the wave function at any future time. But the wave function describes probabilities, not definite outcomes, and so the future is uncertain in a fundamental way. When a measurement happens, when decoherence occurs, the superposition appears to collapse, and we get one outcome out of many possible outcomes. This element of randomness, this irreducible uncertainty, is built into the fabric of quantum reality. Decoherence introduces another aspect of time, another kind of irreversibility. The quantum evolution of the wave function by itself is reversible. If you could reverse all the velocities of all the particles, the wave function would evolve backward in time, retracing its steps. But decoherence is not reversible, at least not in practice. Once information has leaked out into the environment, once entanglement has spread to countless particles, you can't bring it back. You can't undo the decoherence. The environment is too large, too complex, and the information is too dispersed. This is similar to the second law of thermodynamics, which says that entropy, roughly speaking disorder, always increases in an isolated system. Decoherence is a kind of entropy increase, an increase in entanglement entropy, a measure of how much information about the system is hidden in the environment. And just as the second law gives time a direction, an arrow pointing from past to future, decoherence also contributes to this arrow of time. It's one of the processes that makes the past different from the future, that gives time its forward flow. Some physicists believe that the arrow of time, the asymmetry between past and future, is ultimately explained by the special initial state of the universe, by the fact that the universe began in a very low entropy state and has been evolving toward higher entropy ever since. Decoherence fits into this picture as one of the mechanisms that drives entropy increase, one of the ways the universe becomes more disordered, more spread out as time goes on. But these are deep waters, and we don't need to swim too far into them. Just let the ideas float by, like driftwood on a gentle current. The point is that decoherence is connected to some of the most fundamental aspects of reality, the nature of time, the emergence of classicality, the relationship between quantum and classical, the structure of the universe itself. Let's think now about experiments, about how scientists actually study decoherence, how they observe it and measure it. One of the most famous experiments involves something called a double-slit experiment, which you might have heard of. It's a simple setup, but it reveals the heart of quantum strangeness. You take a source of particles, electrons or photons, and you send them toward a barrier with two narrow slits. On the other side, you have a screen that detects where the particles land. If you close one slit, the particles go through the other and make a pattern on the screen, a single bright band corresponding to the open slit. If you close the other slit, you get a different pattern shifted to the side. So far, this is classical behavior, what you'd expect from particles. But if you open both slits, something strange happens. Instead of getting two bright bands, one from each slit, you get a whole series of bright and dark bands, an interference pattern, the kind of pattern you'd expect from waves. The particles, it seems, are going through both slits at once, interfering with themselves, creating regions where they're more likely to land and regions where they're less likely. This is quantum superposition in action. Each particle is in a superposition of going through slit 1 and slit 2, and these two paths interfere, producing the pattern. But if you try to observe which slit the particle goes through, if you put a detector near the slits to measure the path, the interference pattern disappears. You get two bright bands, classical behavior again. The act of measurement, the interaction with the detector, causes decoherence, destroying the superposition. For many years, this was explained simply as the collapse of the wave function due to measurement. But with the understanding of decoherence, we can see it more clearly. When the particle interacts with the detector, it becomes entangled with the detector's state. The detector records which slit the particle went through, and this information leaks out into the environment, into the particles that make up the detector. the photons bouncing off it, the air molecules around it. The coherence between the two paths, the two slits, is lost. The particle still goes through both slits in a sense, but the two paths no longer interfere because they're now correlated with different environmental states. Scientists have done many variations of this experiment with increasing sophistication. They've used atoms instead of photons, molecules instead of atoms, even large organic molecules with hundreds of atoms. In each case, they see the same pattern. Small, isolated systems show interference. Larger systems, or systems that interact more strongly with their environment, show less interference or none at all. Decoherence sets in faster for larger, more complex objects, exactly as the theory predicts. There are also experiments designed to study decoherence directly, to watch it happen in real time. Physicists create quantum superpositions in carefully controlled systems, like trapped ions or superconducting circuits, and then they introduce interactions with the environment, either deliberately or by failing to fully isolate the system. They measure how quickly the coherence decays, how the interference fringes fade, how the quantum state becomes classical, and they find excellent agreement with the predictions of decoherence theory. One of the challenges in these experiments is that decoherence usually happens very fast, much faster than other processes, so you need very precise control and very fast measurements to observe it. But with modern technology, with lasers and detectors and cryogenic cooling, scientists can now probe decoherence in great detail, watching the quantum to classical transition unfold at timescales of microseconds or nanoseconds, or even faster. These experiments are not just academic curiosities. They're essential for developing quantum technologies, for understanding the limits of quantum computers, quantum sensors, quantum communication devices. If we want to build machines that exploit quantum mechanics, we need to understand decoherence, to minimize it, to work around it, to protect our delicate quantum states from the noisy environment. As you listen, you might notice your breathing, slow and steady, or the feeling of relaxation spreading through your body. There's no urgency here, no need to stay alert. Just let the words wash over you, let the ideas drift in and out of your awareness. We're circling the same concepts again and again, from different angles, like a slow walk around a sculpture, seeing new details each time. Let's return to the idea of the pointer basis, which we touched on earlier. This is a subtle but important concept in decoherence theory. The idea is that when a system interacts with its environment, the environment doesn't treat all quantum states equally. Some states are more stable, more resistant to decoherence than others. These stable states are called pointer states, and together they form the pointer basis. For example, for a particle's position, the pointer basis is usually the basis of definite positions. The environment is constantly scattering photons off the particle, interacting with it in ways that depend on where it is. This selects position as the stable quantity, the one that doesn't get scrambled by decoherence. If the particle is in a superposition of being here and there, the environment will quickly decohere this superposition, making it appear to be in one definite place. But for other systems, the pointer basis might be different. For a spin system, if the dominant interaction is a magnetic field, the pointer basis might be the spin states aligned with the field. For a molecule, the pointer basis might involve certain vibrational modes or energy levels, depending on how the molecule interacts with its surroundings. The pointer basis is not chosen by us, not decided by our measurement apparatus. It's determined by the physics of the system and environment interaction. The environment, in a sense, performs a continuous measurement, selecting certain states as the ones that survive, the ones that become classical. This is why we observe position and momentum and energy as classical properties. These are the quantities that the environment naturally measures, the ones that decohere most readily. This connects to a famous principle in quantum mechanics called the uncertainty principle, discovered by Heisenberg. The uncertainty principle says that certain pairs of quantities, like position and momentum, cannot both be known precisely at the same time. If you measure position very accurately, you necessarily disturb the momentum, and vice versa. This is not a limitation of our measurement devices, but a fundamental feature of quantum reality. Decoherence and the pointer basis add another layer to this. They say that the environment naturally picks out certain quantities as the ones that become definite, the ones that have classical values. Usually, these are position-like quantities for particles moving in space, or energy-like quantities for isolated quantum systems. But momentum, which is complementary to position in the uncertainty principle, does not become definite in the same way. It remains quantum, uncertain, because it doesn't decohere as readily. This asymmetry, this selection of certain properties over others, is what gives the classical world its particular character. We live in a world of definite positions and energies, not a world of definite momentum and phase. And this is because of decoherence, because of how systems interact with their environments. There's something almost poetic about this, the idea that the classical world we experience is not arbitrary, but selected by the environment, by the web of interactions that connects everything to everything else. We are shaped by our environment, not just biologically and psychologically, but even at the level of the physics that makes our experience possible. Now let's think about consciousness, about the mind, about the role of observers in quantum mechanics. This is a fraught topic, one where physics touches on philosophy and where many people have strong opinions. In the early days of quantum mechanics, some physicists, notably Eugene Wigner and John von Neumann, suggested that consciousness might play a special role in collapsing the wave function. The idea was that only a conscious observer could truly make a measurement, that the chain of quantum interactions had to terminate in a mind for the collapse to occur. This view has largely fallen out of favor, at least among physicists, because it seems to give consciousness a privileged role in the laws of physics that's hard to justify and hard to reconcile with what we know about the brain and biology. Decoherence offers a way out. It explains the appearance of collapse without requiring consciousness, without requiring any special observer. The environment does the job, automatically and unconsciously. But this doesn't mean consciousness is irrelevant or unimportant. It just means that consciousness is not necessary for decoherence, not necessary for the quantum to classical transition. Consciousness arises, presumably, from the complex workings of the brain, which is itself a classical system, at least at the level where neurons fire and synapses transmit signals. The brain is subject to decoherence like everything else, and the quantum coherence within it, if it exists at all, is very limited and very short-lived. Some people find this disappointing, as if decoherence removes some of the mystery or magic from the universe, as if it reduces mind to mere mechanism. But there's another way to see it. Decoherence makes the world stable, reliable, predictable enough for complex structures like brains to exist and function. Without decoherence, without the emergence of classical behavior, there could be no stable information processing, no memory, no thought, no consciousness. So in a deep sense, decoherence is not the enemy of consciousness, but its precondition. We are quantum beings living in a quantum universe, but we experience a classical world because we are large and warm and coupled to a vast environment. Our thoughts, our perceptions, our sense of self, all of these arise from processes that have long since decohered, that have left the quantum realm behind and entered the classical domain of neurons and chemicals and electrical signals. And that's not a loss. It's a kind of miracle that such complexity and awareness can emerge from the simple laws of physics, from the interplay of quantum and classical, of coherence and decoherence. Let's drift back now to the mathematics, just briefly, not to get lost in equations, but to appreciate the structure, the elegance of the theory. Decoherence can be described very precisely using the mathematical tools of quantum mechanics: density matrices, partial traces, reduced states. If you were to study this in detail, you would learn how to calculate the decoherence rate, how to predict which states will survive and which will be washed away, how to model the environment and its effects. But you don't need to do that calculation to understand the essence. The essence is that quantum states are fragile, that they depend on coherence, on the precise alignment of phases, and that interactions with the environment disrupt this alignment, spreading the information out, entangling the system with countless particles. The mathematics makes this precise, quantitative, predictive, but the idea itself is almost intuitive once you grasp it. There are also connections to information theory, to the study of how information is stored, transmitted, and lost. Decoherence is, in a sense, a process of information loss, or at least information hiding. The information about the quantum state doesn't disappear from the universe, but it becomes inaccessible, encoded in the environment in a way that we can never fully retrieve. This is similar to what happens when you scramble an egg. The information about the original arrangement of molecules is still there, in principle, but it's so scrambled, so mixed up, that you can never unscramble it and get the egg back. This connection between decoherence and information, between quantum mechanics and thermodynamics, is an active area of research. Some physicists believe that information is the fundamental concept, more fundamental even than matter or energy, and that the laws of physics are really laws about how information flows and transforms. From this perspective, decoherence is a kind of information flow from the system into the environment, and the emergence of classicality is the emergence of certain stable patterns of information. These are speculative ideas, still being explored, still being debated, but they hint at a deeper unity, a way of understanding physics that connects quantum mechanics, thermodynamics, information theory, and perhaps even gravity and spacetime. It's a beautiful vision, one that many physicists are working toward, trying to bring together the different pieces of our understanding into a single coherent framework. You might feel yourself drifting closer to sleep now, or perhaps you're already in that hazy space between waking and dreaming. That's perfectly fine. There's no need to hold on to anything, no need to remember or understand. Just let the words be a gentle presence, a quiet voice in the background, like rain on a roof or waves on a distant shore. Let's think about the universe again, about the vastness of space and time, about the billions of galaxies, each with billions of stars, stretching across distances so large they make the mind reel. All of this immensity is governed by the laws of quantum mechanics, the same laws that govern a single electron spinning in an atom, and yet we see a classical universe, a universe of planets and stars and galaxies, not a quantum blur of superpositions. Decoherence is the reason. Every atom, every particle, every wave of light, all of them are constantly interacting, constantly entangling with their environments, constantly decohering. The universe is full, not empty. Even the emptiest space, the darkest void between galaxies, contains a faint haze of photons, particles, quantum fields, all of them interacting, all of them contributing to decoherence. And so the universe appears classical, appears definite, even though at its heart it's quantum. This is one of the great achievements of 20th century physics, to understand how the classical world emerges from quantum foundations, to see that there's no contradiction, no conflict, just a beautiful subtle transition mediated by decoherence. Some have asked, if everything is quantum, if the universe is described by a single vast wave function, then what is the environment? What is outside the universe? This is a deep question, one that touches on the foundations of cosmology and quantum theory. One answer is that the universe as a whole has no environment, nothing outside it to interact with, and so it doesn't decohere. The full quantum description of the universe remains quantum, always, in all its complexity. But we, as subsystems within the universe, do have an environment, the rest of the universe. And for us, for anything smaller than the whole, decoherence happens, and classicality emerges. So the universe as a whole might be quantum, might exist in a vast superposition of all possible states, but we experience only one branch, one small corner of that superposition because we are part of the universe, entangled with the rest of it, decohered from the other branches. This is the many worlds view again, seen from a slightly different angle. It's a way of making sense of the quantum universe without invoking collapse, without requiring anything outside the quantum formalism. And decoherence is what explains why we don't see the other branches, why we experience a single classical reality, even though the full quantum state includes countless possibilities. Whether you find this plausible or not, whether it feels right or strange or unsettling, is a matter of personal inclination. The physics is the same either way. Decoherence happens, coherence is lost, classicality emerges. How you interpret what that means, what the ultimate nature of reality is, that's where physics shades into philosophy, where certainty gives way to speculation and wonder. Let's slow down even more, let the pace become a gentle lull. There's no hurry, no destination, just a slow wandering through ideas, through concepts that have occupied some of the deepest minds for over a century. You don't need to grasp it all, don't need to see the whole picture. Just rest in the knowledge that there is a picture, that people have thought about these things carefully, that the world makes sense even if that sense is subtle and strange. Imagine a photon born in the heart of a star from the fusion of hydrogen into helium. It travels outward through the dense core, scattering countless times, bouncing off electrons and atoms, taking hundreds of thousands of years to reach the surface. Each interaction entangles it with the star's environment, decoheres its state, makes it more and more classical. By the time it emerges into space, it's a classical particle of light, no longer in any delicate quantum superposition. It travels through the emptiness, across millions or billions of miles, barely interacting with anything. Perhaps its quantum coherence begins to recover, slightly, though it's still classical for most purposes. Then it reaches a planet, the Earth, and it enters the atmosphere, scattering off molecules of air, water vapor, dust. Again, decoherence sets in. The photon becomes entangled with the environment. Its state becomes definite. Finally, it reaches your eye, passes through the lens, strikes a molecule in the retina, triggers a chemical reaction that sends a signal to the brain. Each step is an interaction, a measurement, a decoherence. The photon's journey ends, and its energy is absorbed, transformed into the electrochemical signals that become your perception, your awareness of light. This whole process, from star to eye, is a story of decoherence, of quantum states becoming classical, of information spreading and being transformed. And it's happening constantly, for every photon, every particle, every interaction in the universe. It's the background hum of reality, the process that makes the world what it is. There's a kind of beauty in this, a quiet, understated elegance. The universe doesn't need to be conscious to function, doesn't need observers or special rules. It just follows its laws, and those laws, when you include the environment, naturally give rise to the world we see. Decoherence is automatic, inevitable, built into the fabric of how things interact. You might think about your own life, your own experience, as a kind of classical island in a quantum sea. You are made of atoms, and atoms are quantum, governed by wave functions and probabilities. But you are also large, warm, complex, constantly interacting with your environment, constantly decohering. And so you experience a classical world, a world of definite objects and events, even though you are, at the deepest level, a quantum system. There's a paradox here, or at least an irony. You are quantum, yet you never see quantum effects in your own experience. You never find yourself in two places at once, never feel superposed. And that's because decoherence is so strong, so fast at your scale, that the quantum weirdness is washed away before it can ever reach your awareness. But in a way, this makes the quantum world more real, not less. It's not that quantum mechanics is wrong or limited or only applies to tiny things. It applies to everything, including you. It's just that the quantum effects, the superpositions and interference, are hidden by decoherence, buried in the complexity of your interactions with the world around you. Some physicists have tried to imagine what it would be like to experience quantum superposition, to be in two states at once. It's hard, perhaps impossible, because our brains, our consciousness, are classical. We can think about superposition abstractly, mathematically, but we can't feel it, can't live it. Our experience is always definite, always one thing or another, because our neural states have long since decohered. This might seem like a limitation, a barrier between us and the true nature of reality. But it's also what makes experience possible at all. A brain in superposition, if such a thing could exist, would not have definite thoughts, definite memories, a definite sense of self. It would be a quantum blur, unable to process information, unable to form coherent perceptions. So decoherence, by making us classical, makes us conscious, makes us capable of thought and feeling. There's a philosophical tradition, going back to ancient Greece, that tries to understand what is real, what truly exists. Plato thought that the world we see is just a shadow of a deeper reality, a realm of perfect forms. Aristotle thought that reality is in the particulars, the individual things we encounter. Modern physics offers its own answer, subtler and stranger than either. Reality is quantum, but it appears classical because of decoherence. The particulars we encounter, The definite objects and events are selected by the environment, stabilized by countless interactions. This doesn't make them any less real, but it does mean they're not fundamental. The fundamental reality is the wave function, the quantum state, and the classical world is an emergent phenomenon arising from decoherence. It's a bit like saying that a wave on the ocean is real, even though it's just water molecules moving in a particular pattern. The wave emerges from the motion of the molecules, but it has properties of its own shape and speed and energy. Similarly, the classical world emerges from the quantum world, but it has its own structure, its own laws, at least approximately. This is sometimes called the doctrine of emergence. The idea that higher-level phenomena can arise from lower-level processes without being reducible to them, at least not in a simple way. Life emerges from chemistry, consciousness emerges from neuroscience, and classicality emerges from quantum mechanics through decoherence. Each level has its own principles, its own patterns, even though it's ultimately grounded in the level below. You can rest in this thought if you like, or let it drift away. There's no need to decide what's real or what's fundamental. Just let the ideas be there, like clouds drifting across the sky, present but not demanding, beautiful but not insistent. As we come toward the end of this long, slow exploration, let's return once more to the beginning, to the simple question, how does the quantum world become classical? We've circled this question many times, from many angles, and the answer is always the same: decoherence. Interaction with the environment, entanglement, the spreading of information, the loss of coherence. It's a process, not a moment, gradual, not sudden, natural, not mysterious. Decoherence explains why Schrödinger's cat is never both alive and dead, why we don't see tables in superposition, why the moon is there even when no one is looking. It explains the stability of the macroscopic world, the definiteness of outcomes, the emergence of the classical from the quantum. And it does this without invoking consciousness, without requiring observers, without any magic or mystery beyond the quantum mechanics itself. Of course, decoherence doesn't answer every question. It doesn't tell us what the wave function really is, whether it represents something physical or just our knowledge. It doesn't tell us why there's something, rather than nothing, why the universe exists at all, why the laws of physics are what they are. These are deeper questions, perhaps beyond the reach of physics, at least for now. But what decoherence does do is remarkable. It bridges the gap between two worlds, the quantum and the classical, showing how one gives rise to the other through a simple, inevitable process. It removes the need for ad hoc assumptions, for special rules about measurement and collapse. It makes quantum mechanics more complete, more satisfying, more beautiful. And there's something comforting in this, something reassuring. The world makes sense. It follows laws, deep laws. And those laws, when you follow them carefully, explain the world we see. There's no need for special interventions, no need for the universe to care whether we're looking or not. Things just are, and decoherence is part of how they are. As you drift now, perhaps towards sleep, perhaps just toward a quieter state of mind, let these thoughts settle gently, like dust after a long journey. You've traveled through ideas about particles and waves, superposition and entanglement, measurement and environment, coherence and decoherence. You've seen how the quantum world, strange and probabilistic, gives rise to the classical world, stable and definite, through the simple process of interaction with surroundings. This is the story of quantum decoherence, told slowly, told gently, with no urgency and no demand. It's a story about the fabric of reality, about how things work at the deepest level, about the subtle dance between possibility and actuality, between the quantum and the classical. And it's a story that continues, always, in every moment, in every particle, in every interaction throughout the vast reaches of space and time. There's no need to hold on to any of this, no need to remember the terms or the concepts or the arguments. Just let it be there. A quiet background, a sense that the world is knowable, that people have thought deeply about it, that there are answers, even if they're subtle and strange. And as you let go, as you release the need to understand or to follow, you can simply rest, knowing that the universe is what it is, quantum and classical both, woven together by decoherence into the seamless whole we call reality. The photons continue to scatter, the atoms continue to vibrate, the particles continue their endless dance of interaction and entanglement. Decoherence happens, moment by moment, washing away the quantum interference, revealing the classical world beneath. And in this process, in this quiet, automatic unfolding, the universe becomes what it is, becomes the place where stars shine and planets turn, and thoughts arise and fade like waves on an endless ocean. Rest now, if you'd like, in the knowledge that all of this is happening, has always been happening, will always be happening, whether you think about it or not, whether you understand it or not. The world doesn't need your attention to exist, doesn't need your comprehension to function. It simply is, and decoherence is part of how it is, woven into every interaction, every moment, every breath. And so we end, not with a conclusion, but with a fading, a gentle release, letting the ideas dissolve back into the quietness from which they came, leaving only a sense of vastness, of time, of the beautiful strangeness of being part of this quantum universe that appears, to us, so wonderfully, reliably, comfortingly classical.